is a very well-known person within the computer vision field. He got his PhD from Oxford University. After that, he did a postdoc at the MIT, and currently he is associate professor at New York University, and he also works as a research scientist at Facebook AI Research. So please join me in giving a very charming welcome to Rob.
Can you hear me? Does it sound good? Okay. So deep learning is quite a big area, and I'm supposed to give 3 talks. So I thought what I would do is, this first one is going to be fairly focused on just more of an introductory thing, and then get on to sort of more advanced topics in the next 2. So just to look at an overview of this first lecture, I'm not sure how many of you are sort of super into deep learning, so I thought I might do a sort of very general high-level overview initially. So apologies if this is sort of, you've seen all this stuff before. And then we'll look at a bit more detail in one particular type of deep network called convolutional neural net. And then we'll look at some sort of developments on that idea, some sort of residual networks, and then finally we'll just look at some sort of practical application that we're using these things for in industry. Okay, so pretty much everything in this first lecture is going to be entirely about supervised learning. Okay, so subsequent to, I'll try and look at sort of more interesting things about supervised learning. Okay. Perfect. So just to start out, so everyone's super excited about deep learning at the moment. There's a lot of papers and sort of buzz in the media and so on. To be honest, this is really the sort of a reincarnation of the sort of you can think of this as like neural nets 3.0. Okay, so really neural nets began a very long time ago, just after the Second World War. There were people who were sort of thinking about how to instantiate. Looking at the brain and trying to think about how to create sort of artificial neurons and stuff like that. And so they were creating these very simple things, which would, essentially just, simple neurons that would just help you use multiplications and summations and some kind of simple non-linearity to do basic things. So actually, there's something called perceptron, which is like a sort of singular neural net. These guys were building, back in those days using completely, obviously, crazy primitive hardware that was available from them at the time. And the basic philosophy behind this whole approach of neural nets is called connectionism. And the idea is if you connect a whole bunch of these very, very simple computational units, like these artificial neurons together in the right way, then you can get interesting complicated things arising. And this is, in contrast to something like sort of, logical representations where you're trying to reason with logic, which was, of course, another very prevalent approach throughout the history of AI. Okay, so this was, there's some very interesting kind of work done in these early days. They were very much limited by the hardware. They didn't know, of course, how to do anything with more than a single layer. So there was some interesting theoretical results showing that the limit to what you could do with a single layer, that kind of in practice, hampered much of the research in the field for a while. And then there was a sort of, a revival, sort of neural nets 2.0, that happened in the mid-80s. So basically people figured out how to train networks with more than one layer in a principled way. So this is a backpropagation algorithm that you've probably heard of. Backpropagation is a fancy word for the chain rule, essentially. And during that era, people came up with certain architectures that were sort of perhaps particularly well adapted to certain types of modality. So for example, for images, this thing called a convolutional neural network that we're going to look at in quite a lot of detail later on. Was invented by Jan Kuhn, who's now very widely known. And what's interesting is that this architecture sort of more or less persisted, to the current era. So it's proved, even back then they were able to do some quite interesting applications with it, but now it's sort of really exploded with, as we'll see, with a bunch of modern compute power and data and so on. Okay, so the sort of deep learning era that I'm going to talk about really is, as I say, I really think there's a sort of third reincarnation of neural nets. Starts, I guess, in around about 2011. Some Japanese students had some pretty big successes in applying the deep nets for speech understanding. So this is trying to recognize phonemes in spoken speech. And then in 2012, there was a lot of breakthroughs in vision, applying again big deep net models. So essentially there are three ingredients that really quite in common to a lot of these breakthroughs. So let me just, before I get there, there's also some incredible advances in NLP. Now I'm not actually going to talk about those really at all, just because that's what Kyung-Young Cho, who's the next lecturer, is going to talk about in depth. Okay, so just to make sure we don't have too much overlap. So I'm going to focus really mainly on the visual stuff, just as it's easy to present and sort of a bit closer to my background. But Kyung-Young is going to present more sort of deep nets applied to NLP. But the basic sort of recipe of underlying models are actually pretty similar across these different types of different modalities. So the three ingredients really that sort of made things a big success was these very deep models that we're going to look at. And what's I think surprising is that really, they're in many ways really more or less the same models we had back in the mid-80s, just bigger. And they can be bigger because now we have fast GPUs we can use to implement them on. And then the third thing, which I think has also been very important, was the fact that we have really pretty large labeled data sets available on a scale which we just didn't have before. It's also worth mentioning there has been some pretty exciting other progress on some other AI tasks as well, outside just sort of conceptual problems. And I think that's obviously what the future, but it's a lot of future progress lies, and I'll talk to that tomorrow a bit. Okay, so just look at those ingredients in detail. So there are data sets like ImageNet, so obviously one well-known one, and Coco as well. So these are things where they've essentially crowdsourced annotation of lots of images that they've gathered off the internet. These are sort of real-world images. They're not sort of artificial ones that people had previously in data sets. And they're big in the sense of millions of examples, not just a few hundred examples for each different object category. That, in practice, really enables, if you only have a few hundred examples per category, you can't reasonably train a huge deep net model successfully. It's just no one knows how really to do it. If you have, on the scale of 1 million images, then somehow things change and it really starts to work. The other components I mentioned was the sort of the fact that you have these GPUs. It turns out that deep nets are just the basic operations you need to do in a deep net, like matrix multiplies and convolutions, are fantastically easily implemented on these GPUs. They can be parallelized very effectively. And so this slide I raised now is out of date. So common world latest performances of the Pascal is now a couple years old. But the point is that a single one of these cards is delivering sort of many tens of teraflops now performance. And even just this was the sort of, I guess, a couple of years ago state-of-the-art card. That was faster than the fastest supercomputer in the world in 2000. As a point of reference, which it would cost taking up a whole full room. And just to go back to the sort of previous neural network era, they were using some workstations. And Jan LeCun posted some comment that I looked at in detail. And he was pointing out that these latest generation cards are 10 million times faster than the machines he had available when he was designing the first ConvNets. So Moore's law compounded up over a couple of decades really equals huge performance gains. And that really means you can have these massive models. So this is an example of one. So this is a particularly famous one. This was some students from Jeff Hinton's group, Alex Brzezski and Yusuf Skava. This was a type of convolutional neural net. Again, we'll look at the details of this in due course. But basically, it's got sort of 8. This is the input image that's presented here. It's sort of 224 by 224 resolution, and it has a series of these different layers of the network where we're computing kind of features using these sort of simple neurons, as it were, and then we're computing successively more sort of abstract features up through the network. And then at the top, we make some sort of prediction as to what category of object is in the image. Okay, so this thing has a lot of free parameters, free weights that are going to be updated in training through backpropagation. So the idea is you make some prediction, you're going to compare that to a ground truth label, and then you're going to backpropagate the error signal through here to update the parameters, which, as we'll see, will be the convolutional filters in the network. So this thing had about 60 million free parameters, trained on 1.2 million images. It took them, this was 2012, about a week on a pair of GPUs. So it was a pretty epic training moment. It's worth pointing out that these days there are papers coming out showing you can train these similar architecture in a matter of a few sort of tens of minutes on the same data set. So there's been both big speed ups of GPUs and also improvements on sort of parallel training techniques, which I'll talk to at the end of this lecture. Okay. So just to sort of contrast a little bit the deep learning stuff from sort of traditional recognition approaches, and this is I think also true of other modalities as well. In the pre-deep learning era, what happened essentially was you take your image, you would have a whole bunch of handcrafted feature extractors, so things like SIFT and HOG. These would basically would look at sort of, for example, histograms of oriented edge energy and stuff like that. So these were designed by hand, and that would give you some sort of high-dimensional representation that you could throw into your favorite classifier, SVM or whatever, and that would then make a prediction as to what class was in the image. And the key point was that in some sense, when you said you trained your model, all you were really doing was just, modifying the weights of this classifier at the top. Okay, so the feature representation didn't get learned at all. Okay, that was really just handcrafted. And people had managed to figure out sort of maybe, effectively sort of 2 layers of feature extraction that seemed to, work quite well, but they couldn't really figure out, what to do beyond that. And so from a, conceptual point of view, what's really happened with DeepNet is you're now making all the layers of the model trainable. So you're training the feature extractor as well as the classifier that's just sitting on top. Okay? So you train this whole thing kind of end to end. And that's, in practice, seems to be sort of crucial to doing this. So it just turns out that our intuitions about what kinds of features you should try and extract just isn't that great. You should really just try and learn it. So that's the sort of high-level philosophical point. We'll take a message really from this. We've got these breakthroughs in learning. Okay, so just to say, so this was the sort of the pre-deep learning era on this competition called ImageNet. This was a benchmark competition they ran every year. You had to sort of label, make predictions over 1,000 classes. They had some error-metric, and the sort of error rates were sort of around 25–26%. They hadn't gone down a whole lot before then. They'd run for a few years before. So the things were improving. The state-of-the-art methods used a whole menage of these sort of handcrafted features. And then what happened was that paper that model I alluded to earlier from Alex Fergus and others came in and got a big reduction in error rate. And what's I think perhaps equally impressive is that in subsequent years people managed to modify the architecture of those neural nets. It's still the same basic underlying supervised deep neural net model, but they've managed to sort of crank the error rates down. Now, I haven't got the latest results now on ImageNet classification, I think, are under 3%. So that's, it's gone from essentially, in practical terms, not really being useful for that much because the error rates are pretty high, to being, as we'll see, I think I've got the thing here, right, exactly. So it's a slightly artificial task. Humans aren't sort of usually typically asked to sort of categorize in this sort of formal way. But when some, one of the ImageNet organizers did that himself for doing it, he got an error rate that was about 5% or something like that. So these models, at least in this sort of somewhat limited setting, are sort of really, doing pretty well compared to humans. And this is, all happened in just a few years. Okay, so what's sort of, what's changed within the architecture? So obviously the non-deep learning ones were kind of in a shower in some sense. The Alex Fergus model, AlexNet as it's called, at 8 layers. This was another model that one of my students, in fact, was the winner this year. It also had 8 layers. And then a lot of the big gains then came by just making the models deeper and deeper. Okay, and so in this case, they were able to get it deeper, and as we'll see, this sort of depth is really sort of crucial to getting this good performance. Now in this case, they were able to do it by sort of just re-architecting, existing model, use fairly standard, still using standards to train things. This one we're going to cover in much more detail. So this was really re-examining the basic computation that goes on in the networks and changing exactly how they work. And it turns out there's some very interesting kind of optimization issues that come in once you start trying to push beyond this with standard techniques. And you can't get to this sort of depth of network without really changing the way the networks operate. So that's what we're going to talk about in the second half of this lecture. Okay, so just to sort of give you a hand-wavy sort of intuition about why the depth is important. So the idea is that each layer is implementing a little non-linear function. It's going to give you a little decision surface. You just take a single layer model, it's going to give you in this little toy example a kind of linear decision surface. You can clearly see that in this little example, it's being there isn't a simple linear separation for 2 classes. So you need to have a much more complicated decision surface. That's the thing in purple. And then in this case, this is a visualization of a 3-layer neural net trying to sort of carve out the space to sort of classify red versus blue. And the idea is that as you get each layer you bring in, you get this sort of composition effect. So you can end up subdividing the decision surface that you already had from the previous layers, and in practice that lets you implement these very, very complicated kind of decision surfaces. And this is just a simple low-dimensional example, but if you're in some kind of high-dimensional space and you're trying to separate cats versus dogs, you're clearly going to have a very complicated decision surface to do that. And so, in practice, this seems to be, the depth does seem to be crucial, like much more so than things like the width of the network or how many parameters they have and stuff like that. And so part of that is also, so when you have these very deep nets, you can see that they're learning in the intermediate stage some very interesting kind of features that are very sort of, interestingly abstract. You can find feature maps here, which these are looking at little patches that cause a particular feature map to respond strongly in the model. You can see here, this one seems to like text on the side of objects, and this one likes sort of concentric structures. And you can see that the kind of invariances it's capturing here would be incredibly difficult to kind of handcraft manually. So, so we're going to look at, we'll visualize things a bit more in due course. So just to give you a sort of feel, at least in the image domain, where things are. So this is a sort of fairly, this model's a couple of years old now, but it's still pretty close to state of the art. So this is just a typical image. In this case, the model's outputting a bounding box on each, where it thinks the object is, and it's attaching a little confidence to it as well. And you can see it's doing pretty well. Like even sort of included objects like this person here, it's pretty confident about. It doesn't miss one or two things, like umbrellas or whatnot. Possibly that wasn't one of the categories that the thing was trained on. But you can, these are complicated real-world scenes that the model can do really well on. This is another one, so you can see here quite different viewpoint invariances. Motorcycles here, sort of end-on motorcycles over there. Very different lighting conditions in some parts of the image, and still doing pretty well. And so on. And then this is I think my video is going to play. Okay, so this is done frame by frame. So this is one of the sort of state-of-the-art methods. This is where they're outputting a skeleton on the individual. So there's no temporal smoothing on this, as far as I'm aware. You can see the thing's able to handle really quite complicated deformations of the body, as well as segmenting pretty accurately. So these models actually, I'll sort of, I'm not going to talk about this directly, but these models also, I'll just stop the thought. There's another little, there's a more really complicated scene. So you can see, it does lose the person there. So you can see it's sort of finding, little small people hanging on the Okay, so just talk about some of the other modalities for a moment. So speech has gone through a sort of similar revolution. For decades, really decades, everything was very much oriented around these Gaussian mixture models that recognize individual phonemes in the speech waveform. Then you would have some sort of HMM on top that would make some kind of language model. And these days it's all sort of really combined into a deep neural net. So the first thing to notice is for a given amount of training data, there's really quite a significant reduction in error rates. This is word error rate here. But what's also interesting, I think, is that as you increase the amount of training data, these traditional methods, which are fairly light in terms of numbers of parameters, they improve, but only slightly, right? The slope of this line is not too steep. But the deep nets, because they've got this sort of big capacity, can absorb that sort of all this extra training data. You can see that the error rates continue to drop, and that the gap over here is much bigger than it was over there. So in this era where if you do have these very, very large data sets available, then the deep nets really can sort of leverage them in a way that a lot of the standard, sort of the older, more traditional things do. So this is just a little example. This is again, I guess, a few years old now, but this was one of Baidu's sort of commercial systems that they had. This is translating spoken speech. You can see it was an 11-layer model, 100 million parameters, trained on some 12,000 hours of speech and so on. So huge, huge model. And these are various benchmarks, I guess. So obviously it takes a slight pinch of salt because they're probably deliberately trying to sort of optimize for these scores. So these are sort of, I guess, two versions of the model. This is error rate, and that's humans, like that. So you can see that, some of these benchmarks anyway, they're doing, a bit better than humans do. And then, Kingdom shows going to talk much more about this, but things like, in natural language processing, there's been a lot of interesting developments there. Machine translation is one particularly interesting one. So the architectures they use there are things called recurrent neural nets, which are different to ConvNets. They sort of, they're designed for signals where you have a sort of temporal sequence inherent, like for example, a sentence in English here at the bottom, and this neural net kind of ingests a sentence and effectively reduces it to a single high-dimensional vector that summarizes the entire sentence, and then that's what's called the encoder part of the model, and then there's a decoder part, which then transcribes this back into, in this case, a target language, which is French. This will be the sort of French decoder that takes that sort of, sentence embedding, and then, emits words at the output. And so, a lot of the commercial, there's been big gains in blue score, which is the metric that we use in machine translation for, using these models. And so if you use like Google Translate at all, then these things, these kind of models are happening. Yes, and so one of the, you also see in language modeling, this is where you're trying to sort of predict the next word, given the previous ones, and you can try and ask this model to sort of just generate random sentences, and you can get a feel from the sort of sentence it generates as the sort of, level of fidelity of these things. Okay, so these things, if you look at it locally on the scale of a few words, actually, it looks pretty believable. It's only once you get to the sort of sentence levels that it start looking like garbage and not really making sense. But the point is, these models, these language models in particular are ones where they have trained basically these deep recurrent neural net models on insane amounts of data. So, for example, billions of words of Google. And this is a particular error metric we use in language modeling is complexity, which is roughly how many different words you think, could possibly be, could the next word possibly be. So if you had a perfect model of complexity 1, so this thing is down to sort of below 13 or so. But these are, again, absolutely massive deep nets. Okay, so just run through some practical applications of this stuff. As I said, Google Translate, Facebook also uses these things, and of course, a lot of these internet companies are running these models at huge scale. So what's very nice about these models is, even though at training time, they're kind of complicated to train and a bit of a pain, the nice thing is at test time, they're very lightweight, okay? So you can, with good engineers, you can get these things implemented on a smartphone pretty efficiently. Even, you can also implement them on sort of, compute servers that these big tech companies use, so that you can crunch through, really huge amounts of, examples without, needing, thousands and thousands of servers. So, these things scale very well in a practical sense, and this is just an example of that. In terms of image recognition, so a lot of the tech companies use them for kind of removing hate speech, violent content, offensive content, whatever. They also use them for sort of nonsense pictures. So everyone does that. And then, as I said, the speech recognition systems, if you ever use Alexa or as an Amazon gadget, or your smartphone almost certainly has a deep net speech recognition system in it. And then so these also open up, I think, a lot of other applications which people talk about now. So things like self-driving cars. When they first started out, the vision systems weren't reliable enough. Everyone was using LiDAR. These days, of course, people really are relying both on LiDAR and also on cameras. And of course, it's ConvNets that are doing all these deep nets, basically, that are doing the detection of other vehicles and pedestrians. And then I think also, some pretty interesting stuff. There's a lot of very interesting things coming out now where people are using these deep models in a whole range of scientific applications. So it's not just these sort of more engineering-oriented things, but things like particle physics. People are using them at CERN to try and detect Higgs boson and whatnot. Astronomy is an interesting area where people are using too, and designing molecules is something that people have tried now, and also medicine. So I just showed you a couple of examples I grabbed. So this is, I think, a paper from the Google folks. This is looking at skin cancer, so you present a little image, cropped image here, a particular model on someone's skin, and you want to say, what particular thing it is, and of course they get expert dermatologists to go and do this, to provide the training data, and then they can sort of, test the performance of their system versus, those dermatologists. So if I understand, the red dots here are individual dermatologists, and then the blue curve is the system. So you can see for some of these, the blue curve is actually, you want to be in the top right, so Rex is doing basically about as well as any of only the best dermatologists probably is best few dermatologists that can comparable performance to the system. So in these sort of limited domains where you can get a lot of data, these things do pretty well. Skin cancer, and then another one is diabetic retinopathy. This is a disease of the retina, which causes the cells to die off and make people go blind. There's a whole bunch of these sort of telltale signs that if you go to do an eye exam, they can take a picture like this. So that's bad, that's good. And again, yeah, people have shown this again. I think ophthalmologists, the little dots, can show that these deep learning systems are comparably good to things. And of course, it's a big help because there are many situations where many countries where there aren't enough well-trained ophthalmologists, and so you could have the deep learning system screen patients and then only direct the ones where there was some suspicious signal to the actual clinician. Okay, so there's a little sort of pep talk. Now let's just talk about more serious things. So there's a lot of excitement about deep learning, but there's definitely a lot of problems with it too. So I think first and foremost, we don't really have there's very little in the way of a theoretical understanding of what they're doing. And certainly if you want some performance guarantees, like your self-driving car, you might want some sort of assurance that it was actually going to work at a very, very high level of accuracy. But you can't provide that, unfortunately, at the moment. So they're essentially largely black boxes, which makes it very hard to understand. And I think one of the big problems is that because they're non-convex by nature, a lot of the mathematical tools that we might use to understand this other types of machine learning system, unfortunately go out the window. And also the very high dimensional too, which complicates things as well. So I think this is I would say a huge area at the moment where there's a clear disparity between experiment and theory. A lot of very smart, the good news I guess is there's a lot of very smart people in the theory community who are now looking at these things and trying to understand what else is going on. So a lot of physicists are pretty intrigued as well. So hopefully that gap can be closed a bit, I think, because it really feels things are just too empirical. You really want some sort of underlying scientific understanding of what they're doing. The other thing I was sort of saying just a moment ago there is that it's hard to sort of, these black boxes, it's hard to kind of probe inside the deep net and work out really what on earth's going on. I think, this is just in contrast with some, other types of machine learning, like graphical models, where you do have, a very clear instantiation of what each node really means. And, you don't really have that in the deep net. So you can find a particular, feature map response to dogs or something, but it's a bit unclear as to what conditions and, what does it translate to in terms of sort of, it's not exactly clear what it means. And then I think the biggest issue, which I'm going to talk about, I guess, in the next lecture, later on this afternoon, is this need for lots of labeled data. So, all the things I've been showing you really were just, in some sense, very, very powerful regression functions from, a speech waveform or an image to some kind of human-provided label. And, that's fine in some domains. You can sort of invest the time and energy to get those labels, but it's not always possible to obtain that. There's lots of scenarios where clearly, we will never be able to get millions of examples, and we would like to go to training nevertheless. Okay, so I think a sort of slightly less appreciated aspect of the whole deep learning success story is the fact that the architecture is actually super important. So just at a sort of high philosophical level, previously, as I was explaining, the hand design, the human design element, so what the researcher would spend their time doing was designing the feature extractors, right? Like you design SIP if you were a vision person or something like that. And in deep learning, that's sort of gone away. So what you're doing now is you're learning those features, but you're still sort of hand designing the architecture of the model. Okay? So that is that you're essentially, trying to decide, how many layers should I have, how many feature maps should I have, and stuff like that. And that part of it, so in some sense, all you've done is really just abstract to upper level. And then, of course, I should make a caveat to this point now, because some folks at Google, Barrett Zoff and others, have essentially tried to sort of, use machine learning on that outer loop. So they basically have some sort of reinforcement approach where they would try different architectures, different numbers of layers and so on. And assuming you've got really a lot of compute, like you have at Google, then you can afford to sort of, the inner loop to be a complete training in one of these deep nets. And they have been able to get to automatically devise some pretty architectures that work quite well, I would say. They're probably not, it's not quite clear how they would work in a completely new domain if you had really not too much knowledge. So in some sense, they're kind of limiting the search space of architects that they try to some extent. And I think, so just to sort of go back to this basic point, that if you use a completely generic structure of deep net, that is, if you use a completely fully connected network with no structure whatsoever to it at all, they just generally don't work that well. I mean, it's very difficult to train them beyond a few layers. And secondly, even though in some sense a completely generic structure in theory could learn the convolutional topology that's very successful for images, in practice they just don't do that. And so, what you see is that sort of human intuition at the moment is being used to kind of encode certain certain assumptions about the type of data that you're producing. So, for example, as we'll see, for images, you have the fact that the data points in a regular two-dimensional grid. There's kind of local dependencies and stuff like that. So we'll talk about it just a bit more in a second. And that is sort of baked into somehow the neural net architecture. And so, for example, when you're trying to attack sort of genomic data, it's not quite clear what the sort of optimal structure of the network is that you should do. You could try sort of some kind of current net, but I think my feeling is there's probably still interesting architectures there that are more appropriate to that. So I think things work well, but you've got to remember that people like Jan McCurdy spent a long time back in the 80s figuring out how to sort of build a neural net that was kind of well matched to kind of image structures. And similarly, we were thinking about things like LSTMs and so on. Okay, so on that note, what I was going to do is now, that was the sort of general introduction. Spend a bit of time going into some depth on what a convolutional neural network is. Okay, so this is a picture of Jan McCurdy there. What he looks like. So he came up with this model in the 80s. He was very clearly thinking about how to design a neural net that would be good for images. Okay, and I think what's quite interesting about this is that he didn't sort of just hack around mindlessly. He did actually look at sort of what the neuroscientists had discovered in terms of how the visual cortex operates. So if you look at two famous neuroscientists called Hubel and Wiesel, these guys won a Nobel Prize for understanding what V1 does, which is the sort of first stage of the visual cortex in the back of our heads. And those models, essentially, you have one of these neuroscience models, you have simple cells which are going to be analogous to kind of filtering operations that we're going to look at. And then you have cells which seem to sort of aggregate the outputs of these simple cells. So this is, just looking ahead, this is going to be something akin to kind of the pooling operation that we have in these models. Okay, and the basic idea is that the highest stage of each layer is going to compute. This will be some sort of filtering operation, and there'll be some kind of pooling operation. So I'm going to go into the details of these in just a second. And then these will be repeated many times, and you're computing kind of successfully more sort of abstract representations of the input that hopefully that would be sort of be less dependent on kind of nuisance parameters you don't care about, and more dependent on kind of the class labels you go up there. And of course, this whole thing's been trained supervised, so there's, all the parameters in these filters and stuff like that are going to be set by background gradient. Okay, so just to enlarge on what I was saying there, sorry, the figure has slipped down somehow. The ConvNet really is doing two things. So first of all, it's really exploiting the fact that you have local dependencies. What that means is that if you have a pixel in the center of the image, it's going to be it's only really dependent on some neighboring pixels. And this is just some visualization of that. This is looking at essentially a correlation matrix around, visualized. So if you take an image and you just represent it as a big on vector, and then you take a whole big data set and construct a correlation matrix, and then take a single sort of row out of that and visualize it as an image again, this is really telling you that this central pixel depends really on sort of this small neighborhood here. Like you can see that the magnitude here is the sort of intensity, if you like, and you can see that clearly some distant pixel in the corner of the image is just going to have a very, very good dependency with the central one. Okay, so that means, in practice, that your filters, so some neuron in the subsequent layer doesn't need to connect to all the pixels in the previous layer, just only a little sub-window, is sufficient. Okay, and that's sort of crucial simplifying assumption that is made. The second thing is that things are spatially stationary. So this is the fact that somehow the image statistics should be the same at all different locations of the image, on average, of course. There are some situations where this is not quite right, and you wouldn't really want to do that, like face recognition, one example. You might want to specialize. Once you've got some geometric registration, you might want to specialize the image. Okay, so GAN's ConvNet really could be regarded as this kind of multi-stage Google and Wiesel thing, architecture. So you have these successions of simple layers and complex cells, and then you put this classification there on top. So just, there was a model called the neocognitron from a Japanese researcher called Fukushima, and I mean, he had these basic ideas in there, except that he didn't, this was pre-backprop, okay, so he didn't know how to train the parameters in those models. Okay? So again, he sort of thing really that Yan came up with was using the ideas from here with backprop so you can train these things. Okay, so just to now actually get a bit more depth. Alright, so the idea is this, I'm going to look at sort of each of the components in each layer. The idea is you're going to take in some features. These will be arranged in a 2D, there'll be 2D maps, and you'll have perhaps several of them. So the first layer, you've got just the image, which has 3 different layers, because there are 3 different color planes. But it'll be send 2D layout, including with images. And then you're going to filter this with some dictionary that will be learned. So these filters are essentially the parameters in the ConvNet, and we will learn through backprop. And then the idea is these feature maps, I'll visualize this in a second for you, will be then passed through some element-wise non-linearity. So each element in that feature map will be passed through some non-linearity. And then you will have possibly some kind of spatial pooling operation. You don't typically do this in every layer in the sort of latest models. And then we also interestingly see that you often do some kind of normalization as well can be helpful, particularly for optimization purposes. So I'll go into a bit more detail on that one in just a second. So just to visualize what I'm talking about, here's your input image. This is just grayscale, just to keep it simple. So your learned filter will be something like this. You're going to, the 2D convolution operation is going to slide this all over the image like that, and you get out some response map like so. And the key point is, again, we're stamping down the same filter at each location. Okay, so that hugely reduces the number of parameters in the model compared to just a fully connected network. And then, of course, we have a different filter channel, which will have a different type of filter, and that will produce another feature map. Okay, so the idea is that after the first layer of this, you will have a whole series, stack of these, maybe 32 of these different feature maps. Okay, and then what will happen is you'll pass it through some kind of non-linearity. Okay, so one very common one is something called the ReLU, which has this profile. So this is the input value of a particular pixel from that feature map we just saw, and then this is the output value. So essentially, if your input is negative, the output is 0. If your input is positive, you just it's a density function. So this was the feature map, one particular feature map after the filtering operation. You pass that through your ReLU and you get something that looks a little bit like this. Okay, so you can see now, whereas often with the edges you get this kind of light-dark alternation, here now somehow the dark parts have all been clipped. Just left with somehow signal where the original edge was. And just to say, there's a whole, huge family of these different non-linearities we've tried out. Historically, things like 10x and sigmoid were popular. I think in practice people found those that don't work awfully well. So there's a whole bunch of these sort of ones that are a little bit like ReLU, but a little bit softer, that don't go to 0, makes training easier. This is one where the slope of the line changes. This is one where they have some sort of exponential function here, which kind of smoothly blends here, so we don't have discontinuity at this point here, and so on. So there's a whole bunch of these, and of course everybody claims that their particular flavor, is good for some particular thing. Okay, now pooling, I'm not sure what that's on the slide. So pooling is a sort of operation that's really kind of peculiar to these ConvNets. The idea is that you're going to take a spatial region that you will define beforehand. It's fixed, either on a regular grid like this, it's non-overlapping, or you'll, sorry, my slides are messed up. Or you might be an overlapping grid like this, and you're going to basically take, within each region, you're going to take, typically people just take, to be honest, take a max. I mean, in the old days they tried sums, but I think everyone finds max pooling operations work quite well. There are a few architectures which do something other than pooling, where they do kind of striding convolutions. I'll touch on those in the next lecture. But the basic idea is once you do this, you get some feature map. This is, sorry, for some reason the text is not weird. Basically, this was, I think, this is what looks like the sum, this is what looks like the max. The point is you just reduce the spatial resolution, essentially. So it's not really, you keep the same number of overall feature planes, just the spatial extent is kind of being reduced. Now, one interesting technique that has come in pretty recently that wasn't back around back in the 80s, which I think has proven very effective and quite general for training these things, is something called batch normalization. Okay, so people realized, back in the early days that normalizing, you're doing some pre-processing on your input images was a good idea. So basically that meant sort of making zero mean, possibly whitening them if possible. So that's removing second order dependencies. And so, that was but they weren't doing anything like that in the middle of the network directly. So batch normalization is a trick which basically does some kind of normalization of the data as it passes through the network. So that is, you take a sort of batch here of those feature maps at some midpoint of the network, and then you essentially normalize them. We'll just look at how you do it in just a second. And people have found that this actually really does accelerate training quite considerably and makes the models generally less sensitive to initialization and stuff like that. And that's, so it does seem to be something that's a generally good thing to be doing. And so let's just look at how that works. Okay, so the basic idea is here, you have some, right, so you're going to have some feature map element X, you're going to compute a mean here over the feature map, so that, and over the mini batch. So that's going to be, so the idea is you compute this mean over the mini. Sorry, this is per dimension in fact. So sorry, it's not over all spatial locations. It's a mean across the mini batch. Okay, so when you train this, we'll come to this in a moment. When you train these models, you're going to sort of crunch through not the entire data set of 1 million images in one go. You're going to take little pieces of it and push those through the network. And it turns out to be, more efficient from a memory point of view for the GPUs, but also in practice has a lot of implications for the optimization as well. So you're going to compute a sort of mean for each of the dimensions, as it were, in your feature vector. So even though it's a feature map, you can imagine just turn it back into a feature vector. And you compute standard deviation. So what's really doing here is sort of zeroing the distribution within for each batch, and also rescaling it so that it's sort of now scaled to be sort of unit standard deviation. And then they have these two. So just to be clear, these two mu and sigma are computed from the data itself. Okay, and then they do also seem to have two parameters here, which are then learned, gamma and beta, which kind of reshift and rescale each individual, each channel. So when you're training, the mu and the sigma are computed from the mini batch itself. Okay, so those things are actually computed sort of on the fly. The thing which is complicated then is what do you do sort of at test time? And what happens if you're presenting this as a single image? What do you do? So in practice, you have to sort of then, take some sort of average stat on these from your training set. Hope your test set is sort of roughly some statistics and use those values. So there's a bit of sort of, slight messiness with how you use this at test time. But so this is what we're looking at here is a training curve of accuracy versus sort of training epoch. Or training iteration, sorry. And this is the black curve is if you just have this is a particular type of model. Google folks had something called inception net, where this is the black curve. So you can see that the accuracy is improving, but it's quite slow. It seems to asymptote, around about just a bit below 0.7 accuracy. And then the same model, but with this batch normalization idea, is on this blue curve. So you can see it converges much more quickly. It does actually do better. And these results have sort of held up across a whole bunch of different models and different settings. This seems to be a very generally useful technique. Okay, so just so each layer essentially is going to have these components in. Okay, so you're going to have convolutional non-linearity. Sometimes you'll do pooling. If you're doing classification, then generally you're going to go from some big image down to some sort of high-dimensional feature vector. You're squashing the image down to some feature vector, which is going to be for the class label. So there's pooling operation. You're going to have several pooling operations on route. In practice, because you want to have very deep networks, you're not going to pool with every layer. You're just going to pool with occasionally. If you pool too often, then you can get down to sort of zero, one dimension too fast. And then you have the batch normalization thing, which is often incorporated into sort of little groups of layers and things like that. And then typically what people do is have a very, just a single layer at the top, which is just a fully connected classifier to sort of takes the feature maps, which often are quite small spatial extent, sort of towards the top of the network, and then just vectorizes them into one big high-dimensional vector that you then try to create the class labels from. Okay. And so I'm not going to go into the details of the backprop, so this is something which you can look at online, but the basic idea is that when you backprop through this thing, the things that you end up learning mainly are these convolutional filters that I was talking about, and I guess that the batch normalization does have those scale and offset parameter per dimension, which you can learn as well. Okay. Yeah, sure.
Other than the vertical alteration and batch normalization leads to better do we have a vision for why?
That's a good question. So in their paper, they made this an argument about covariate shift and stuff like this. It turns out, I don't think, talking to the theory people who I know who study these optimization things, they don't really believe that argument in the paper. And so for them, it's still a bit of a mystery exactly why National works so well. So there's a group of Facebook who are sort of looking into these things. And so maybe other people have sort of yeah, that's a great question. So I'm trying to, I'm sorry, I don't remember. In the break I can find out. I did know this, sorry. Sorry. So one thing I thought I'd talk a little bit more in detail about is the training. Because I think this does touch, there's some non-obvious points to this, and there is some sort of quite interesting innovation. And as I was just saying, I don't think it's actually, it's still an open area research. We don't really understand exactly what's going on in these models, what's the best way we can optimize them to train as fast as possible, but not fall into weird minimum and stuff like that. So let's talk about this for a few minutes. So first of all, these models, as I've said, are very big, like some millions of parameters. Now, if you remember you did an optimization class, the model, pretty much in that class, they would say, well, you want fast convergence, you should be using second-order methods. Because then you would be able to sort of, you do much better, you converge much faster than first-order techniques. So the problem is that for a second-order method, you need the Hessian, okay, which is this. So if you have a million parameters, the Hessian, the full Hessian is going to be a million by a million matrix. So you can't even store it in memory. And you still can do funny things like you can compute Hessian vector products without storing the full Hessian. And so that's something you can do reasonably efficiently. But in practice, actually, it's still very difficult to do this. So there's like LBFGS, which is a classic sort of gives you an approximation to the inverse Hessian that you can use. But it doesn't, in practice, work very well with these DNets. Okay. The other point to make is that we've got these huge data sets, right? So what you can, again, the classic way of doing things would be you would want to get the best estimate of your gradient. Let's say we're doing first order, best estimate of your gradient you can. You should run all the data through your model, compute derivatives and so on. And you would then, average those gradients across the full million image data set or something. Now the catch is, of course, is if you do all that work just to make one update to your model, it's incredibly efficient. So the basic idea is first of all, stick with the first order methods. Don't bother with the second order ones. And secondly, just make updates more frequently. So even if you compute that gradient estimate over a much smaller subset of the data, you picked a random, it's still going to be roughly in the right direction. And even if it's a bit noisy, some adults will average out when you're training the multiple iterations. Okay. So this is, simple though it may sound, this is proven actually the most effective, general approach to training these deep nets that people have. Okay? It's called stochastic gradient descent. It's stochastic because if you're taking a small subset of data at each update to compute your gradients over, it will be noisy. It won't be the true gradient direction. So just to, let's actually get the pointer out here at this point. Okay, so the idea is here, you've got some loss function, and for each update t, that loss function will be looking at a sort of subset of the data, the whole thing. So this will be the gradient information you've got for backpropagation, based on your current estimate of your current setting of the parameters p to t. Okay, so that's just the gradients you've got to backprop. Eta is going to be a scalar, so that's going to be some step size, and you're going to use that to compute a sort of update on the parameters at time t. Okay, so that update it's going to be just add that into the current estimate to get the new set of the parameters, and then just iterate this. Now, I skipped over this term. This term is actually in practice one that people often find very useful. It's a momentum term. So the idea is here that if you were moving in the direction previously, it's a good idea to keep generally going in that direction. So the idea is this momentum term is, so this was the update, the previous sort of update you had, and you're just going to have some scalar here, like value of 0.9 or something. So it's going to sort of generally keep going in the direction you went before, but then you're going to sort of obviously blend in the actual gradient information from the current point you're at. Okay, so just talking about how you set these things, so the learning rate in the simplest form of this, we're going to look at sort of variance coming up. This would be a fixed scalar. Okay, you would just set this at the beginning of training. Typically, you want this to be as large as possible, so you make as much, make as much progress as you can, as quickly as you can. Except that if it's too big, you're going to be unstable. Okay, you won't be able to descend into a valley in the energy surface. You'll start bouncing between the walls of the valley, and so on. Now, the momentum terms, I said, that's something that generally seems to help conversions with updates. Most people set the values around 0.9 or something like that. So all the sort of standard software packages that you might use for deep learning, like TensorFlow or Torch, all have these sort of things built in, and they have default values that sort of set usually sensibly. It's worth mentioning there is actually an interesting variation of momentum called Nesterov momentum, which turns out to apply the momentum concept in a slightly different way. I mean, you basically apply it before you do the gradient update. So you put the momentum kind of inside the allocator. So that's the sort of basic SGD. Now, in practice, when you train this thing, what you'll discover is this is a plot here of training epoch. Epoch is one complete pass through the data set. This is error. This is training test, I guess, on some what is this, like ImageNet or something. So this will just, what will happen is the curve will come down and it'll start to flatten out at some point. And what you'll discover is if you're prepared to take that eta parameter that I was looking at here, and you just manually reduce it, make it a third of what it was previously, you'll discover all of a sudden you get another sort of decrease in both training test error and so on. And if you keep annealing them in this fashion, just dialing down the learning rate, you will keep sort of decreasing down nicely. So in other words, somehow varying the learning rate through training seems to be sort of a good idea. Okay, and obviously it's a little bit heuristic doing this kind of manually. I mean, you can try and look at some sort of, when this thing starts to flatten out on my training error, maybe I should try to, reduce the learning rate, and so on. So there's a whole little cottage industry of trying to come up with first-order SGD methods that have some automatic way of adjusting this learning rate. Okay, so I thought we'd just look at a few of them because you'll see them, mentioned in the packages and stuff like that. It's worth talking through. Okay, so the basic idea is the learning rate's going to be scaled per dimension. So there might be some parts of the model where you want to sort of have fast learning rates than others. Basically, this is the update here. So this is the same thing we saw before. I've taken out the momentum term just to make it easy. So this was the update we had previously. We still have a single scalar here, but that scalar is going to be sort of now modified per dimension. This is going to be a vector, the same dimensionality as theta. And the idea is that this will be the gradient you got from backprop. And then this term at the bottom is in some sense a sort of history, right? So it's at the updates, all the updates from the first update you made to the current one of the gradients squared. Okay, so this it's sort of like an RMS average or whatever of those gradients. And so what's going to happen in practice is as you start to move and start to update your parameters, this quantity here is going to sort of grow on the bottom and is naturally going to go and decrease this quantity here. So it's going to sort of downscale the eta. So it's a sort of quite a nice idea. I think in practice it does have a slight problem that this term can only monotonically increase on the bottom. So which means, of course, that the overall sort of amount of updating you're going to do to the parameters is going to sort of decrease over time. And eventually, you basically just stop making progress. Eventually, this whole thing just becomes too small. So that's definitely one sort of famous ones. So one thing you might say is, well, why instead of having the whole history from sort of time t equals the very start of training to the current time, why don't you just have like a moving window or something like that? So you have a sort of moving average. So that's basically what RMS pop is doing. So this is how again has some. So, yeah, I think I've lost some summations as well on the slides. Oh, sorry. It's all hidden down here. Yeah, so this is it's supposed to be a summation of here, some and then one I think that a lot of people find pretty useful is this one called Adam, which is a little bit more intricate, so I'm just going to give the outline of it. There's a very good kind of, someone put together a very good kind of, recent talk explaining what exactly Adam does. So if you want to look at the details, I suggest you go there. But basically, this combines several of the previous ideas, and it's going to sort of compute sort of moving averages of the gradient in this sort of RSS as you go along. Okay? And in practice, most people find like using some optimizer like Adam. So typically these are just switches, you just switch these in the software package. It tends to work a bit better than just plain vanilla SGD for training these models. Now one other thing I sort of glossed over a bit there is I said, okay, you shouldn't use the whole data set to train with for each update. What you should do is take little batches of the data. So then it's an interesting question there. It's like, well, what's the right batch size? So yes, the question then is, what batch size should you use? So the answer is actually, it doesn't seem to matter too much, but it does have a big influence, I think, on efficiency. If you want to do large-scale training, this is something to look at just at the end. You do want to, oh, sorry, I'm shouting. Okay. So this is an interesting paper where they actually looked at how you could train ImageNet in 1 hour. So this was the size of mini batch and that they used during training, and this was the validation error. Okay, so the idea was that you can see that the error rate stays pretty flat even for very, very large batches of data. Okay, so 8,000. So you might say, well, what's the point? Surely the message was to have small batches so you have lots of updates. But it turns out, of course, if you are able to parallelize the training, if you have many GPUs, each of which in parallel are computing gradients on a chunk of the batch, then you can therefore compute each batch. Basically, you can still keep the updates very frequent. And in practice, what they found is that so as you increase the batch size, basically what you need to do is scale the learning rate as well. So in practice, you can get big speed-ups by having larger batches that are spread out over multiple GPUs. So in other words, the whole point here is that batch size doesn't really affect too much in terms of the actual final area you converge to. But if you want to do things like parallel training, you might want to have a large batch size. Okay, so just to this is a sort of set of practical tips that one of my colleagues, Michael Gonzato, wrote down. So this is essentially, you take your wonderful deep net, you try training on your data set, and it doesn't work. And of course, as I said, these models are very black box. What on earth do you do next, right? How do you debug the training? So I thought we were just talking through some of this. So one sanity check you can always do is just take a very small amount of the data, subset of the data, the training set. So instead of the training setting 1 million images, make it 100 images. Okay? Now, if you've got a giant model, you should be able to crush the training error to 0 on that. Okay? If you can't, then there's something wacky with the data, or there's something wrong with the model, or something like that. I would say something like, oh, you've got problems with the backprop, but typically a lot of these software packages, the backprop's on for you. You don't have to do sort of numerical gradient checks. So that's one good sanity check. The second thing is, if the training does give a 0, it means the training diverges. It could be that your learning rate is too large. If the learning is too large, the thing will be unstable, will bounce around, so try to decrease that. As I just mentioned, if you've implemented a new type of layer, which is, does some fancy trick, make sure you do some sort of numerical gradient check. Okay, on that. So we're going to check that the numerically computed gradients match up with the analytic one your function is returning to the back. And the other thing that can happen is maybe you did actually, maybe the loss function you're directly optimizing is really low, but then the accuracy, which is maybe some sort of classification error or something like that, is actually still not very good. Okay, so then that can come about when your loss function doesn't really match the thing you're really trying to actually solve. So obviously you need the loss function is some sort of proxy for the thing you really care about. but we want it's usually something that's differentiable between two gradients. So what you need to look for is in your loss function, is there some sort of weird degeneracy that can take place? Okay, you always need some kind of, you can't just pull everything down. You can't pull the energy of everything down to zero, because then everything would just collapse. You've got to make sure that the loss function will, in practice, when you pull something down, it means something else is going to go up. Okay, so if you're dealing with sort of probabilistic models, that happens naturally from the partition function. Okay, but these deep nets don't have that, so you have to have some sort of alternate thing going on. The next thing is the model not doing very well? Okay, so this is a rather silly point, I have to admit. So this is the sort of deep learning mindset. Okay, so maybe you need a bigger model, basically. So you just make the model bigger, more parameters, maybe it'll work better. There definitely could be some issues around to do with the optimization. We'll look at that just coming up in a second with these residual levels. And then at this point, also somewhat silly too. If the model's too slow, basically says, okay. Okay, so what do these models learn? So you train these things on the, on a big image data set. In the first layer, you can directly look at the filter coefficients. These are the kind of things you learn. You kind of edge filters, that respond to different edges, different orientations and frequencies. You also get some low frequency sort of color abundancy coming up, so this is all, deep nets aren't the only model that produce these things, let me be very clear. But it's all reassuring because these neuroscience people, this is the kind of thing that they found in the cat's visual cortex, and indeed humans have the same thing. So they found these oriented edge detectors, which is really what you're seeing with these kinds of things. So at least first layer anyway, they're doing something fairly sensible. And it's a bit hard to visualize the subsequent layers. One trick we can do is to look for each feature map at a subset of patches in the training set, which just gave very strong responses. Just the absolute magnitude of, the response in the feature map at a particular location was really strong. You can sort of map that back to the image. So for each one of these filters, I've sort of done that here. So you can see, for example, say that this one here is a little sort of high frequency one diagonally. You can see it really seems to like these sort of textured little patches here. Okay, so we can use this sort of visualization trick to look at what the upper layers are doing. So in layer 2, what you see is these models will learn kind of conjunctions of those first layer things, like sort of longer lines. You start to see some sort of circular structures, some interesting textures. It seems to learn and stuff like that. You find this one seems to really like these little eyes, some sort. But interestingly, text seems to be quite popular as well. Yeah. So what I'm doing is I'm in say ImageNet. This is layer 2, so there might be, say, 120 different feature maps, okay? Now each little one group I'm showing here corresponds to patches of input image that gave really strong responses in that particular feature map, okay? So this is feature map number, say, number 32, this will be for feature map number 33, and so on and so forth. And I'm looking at the sort of top 9 patches for across all the input training images that gave really strong responses. Because I can just look at all, for a particular feature map. Let me just draw a picture, it'll be easier. Okay, so the way to think about it is you've got each, this is layer 2, the network. So you've got a feature map which is a certain spatial extent, y, x, and you've got a whole bunch of these feature maps. Okay, so this is feature map number 1, so on this, and maybe 128 or something. So what I can do is, I can run this for a single image. When I compute for a single image input, I will get a set of activities in these feature maps. And of course, if I have a training set, I will have a whole bunch of versions of this feature map. Okay? Each one, this will be image 1, image 2, image 3, and so on. Okay. And so what's going to happen is that I can just take a max over all of this. Right? And I can take, say, the top 9 values in this whole block. And I can say, we say one of the locations was here, but I can go back to the image that this came from, and I can look at the patch that would have generated that particular activation. So the patch is, this is in the feature map. And I mean, it's back in that image. This is the original image down here. This thing would correspond to a little chunk of pixels down here. Well, I mean, yeah, okay, so this is after rectification, so you can just look at the images. Yeah. you did before, you could say, yeah, max absolute values. Yeah, so this is just for one particular maximum, but you could do this for, like, say, 9 of them, which I want to show. Okay, so it just gives you a sort of non-parametric feel for what that particular feature map is kind of responding to in your input domain. Okay, the problem is that the raw coefficients in the second layer don't mean much because they're kind of being applied to kind of the features coming from the first layer, right? Not pixels. So, so for us, it's hard to understand what's going on. Okay, so so as we come up through the model, things get sort of, the receptive fields, because of those pooling operations, as we come up to layer 3 now, a single location here will correspond to a much bigger region of the input image, okay? So that's what the pooling operation typically provides you. It's the fact that you're sort of looking at sort of larger, extensive spatial information of the input. Okay, so now you can see things have started to look a little bit object-like. This one seems to like, heads of birds. This one likes that's one I showed you before, like the text on side of objects and stuff like that. And as you get up to sort of this was one of those AlexNet models, so we only have 5 convolutional layers. The latest ones have many more, but you can see you're learning some quite, things are getting pretty object specific. This one likes keyboards. So what's kind of interesting here is that there's no orientation invariance built into the model, but yet it's still responding, quite strongly to these oriented keyboards. This one likes a detective dog. This feature map I think is kind of cool. So when you look at this, you think, oh, what is this? It's like people or something. And actually, if you look closely, and there's other ways to visualize it, but what you notice is actually the model doesn't care about the foreground objects, it just cares about the water in the background. And if you think about it, if you just had a very simple, any kind of linear operation, would never be able to do that, because of course the foreground objects have much more sort of energy in terms of edge strengths and things like that than the water does itself. Okay, so the fact that it's able to sort of ignore the foreground object and just look for the water in the background, you can only really get deep network with lots of non-linearities. Okay, so how are we doing for time? 20 minutes. Okay. Right. Okay, I can go through some of these things a little bit faster. Okay, so one thing I didn't really talk about when I was talking about training these things was how do you initialize the weights. Okay, so the idea is basically you initialize these things randomly, but that sure, but like what does that mean? So one thing I did want to talk about a little bit here was, and this is an important principle we're going to touch on later as well, is somehow, the distribution of weights will affect how the output, distance of the output depend on the distance of the input. Okay? So it turns out if you just look at these models and if you just throw away the non-linearity because it makes things a little bit more complicated, all right? And just treat them as a deep, multi-layered linear network for a second. This is just a simplifying assumption, so you can just look at the math quickly. If you have some input signal x with a certain variance, then the variance at the end of the first layer is going to be basically the variance of the weights multiplied by this sort of number of inputs, this NA. Okay? So this is just the number of units you have this. This is just simple probability stuff. Okay? Now, if you stack these layers, then you can just simply concatenate. You're going to have a product basically of the terms here. So then the original your input x is going to relate to the output of your multi-layered linear network. Linear, there's no values or anything like that in there, with this following equation. Okay, so you've got a product here, and d is the number of layers. Okay, so that all looks reasonable. Okay, now you can see that what's going to happen, unfortunately, is depending on so that equation holds true there. Now, the backdrop equation, where you're computing gradients and pushing them back through, also has a similar relationship. Okay, so now accept you want to gradient back at your input, your first layer, and then that will be raised now. It's coming in the direction, so it's the number of units of the output of each layer, again, times the variance of the weights, times the variance of your sort of output there. Now, the problem is this, is that if you have to set this very, very carefully if you think about it, right? Because if you set it too big, when you start taking the product here, this quantity is just going to blow up, okay? So this is also what people mean when they say the weights are going to explode. And what's also the flip side, which makes it tricky, is that if it explodes in the forward direction, when you backcrop, everything is going to sort of turn back the other way. So the gradients will kind of vanish and diminish basically to 0. Okay, so you basically have to scale the gradients, scale the weights very carefully, so that essentially the sort of scale factor is going back through the network and remains near unity. Okay? And that will let you do the forward prop successfully and then the back prop successfully too. Okay, so this is the way, if you look at the initializations they typically use in these sort of things like TensorFlow and PyTorch, this is what essentially they're doing, right? They're setting this arrangement up here, so this quantity is equal to 1, yeah, so that you know, is sort of sometimes the correct way to do the initialization. That doesn't set everything. If you, depends if that's on the linear assumption. If you, using ReLUs, then you can assume sort of half of the units off at each layer, so you get this sort of half factor coming into the initialization. Okay, so in practice these things do matter. So when you try to train, a network, if you use in some sense the wrong initialization, this was the one for the linear model, it does, the training error does decrease, but not as much as if you initialize differently. Okay, so just to be clear, right, this is how you initialize the weights at epoch 0. So, okay, so after that you're going to just train with SGD. So this is somehow an initial difference in the way the weights are set up does actually translate to quite significant differences, a long way in the future, even though, of course, you're only making a change right at the outset, which I think is interesting. Okay, and then this is for a 22-layer network. This is a content of 22 layers. And this is one where it could make the difference between not working at all, which would be the blue case. This is an even deeper one. So as things get deeper, they get more sensitive to initialization. And you can see here that with the correct initialization, then things do actually work without that data. Okay, so you might say, well, okay, well, so far so good. We initialize the right way. We do our sort of fancy, Atom optimizer or something like that to try and update. Why don't we just keep making the models deeper and deeper? Maybe the things will just keep working better and better. Okay, so the answer is you get some interesting sort of empirical things you find. So this is on CFAR 10. You can just kind of try and keep making the model deeper and deeper. So typically that just means adding more convolution and non-linearity layers. Right? You typically keep the same number of pooling operations and things like that. Just sort of adding more convolutions and poolings. So convolutions and ReLUs. Sorry, the number of poolings stay the same. So the idea is here, this is training error. This is training error, this is a very important point here. With training error, with 20 layers, you do pretty well, right? Getting that down to a few percent. Now, if you make the model deeper, which means it has more parameters, it actually gets worse. Now, this isn't overfitting, to be clear, right? This is the training error is less good. So this is an optimization problem, basically, right? And it's the same story is actually true in test error too. So in this case here, the test error is, again, pretty good, just around 10%, but it actually gets worse than you think. So if you just saw that, you might say, oh, that's just overfitting too many parameters. But in training, you should expect the deeper model to have lower training error than the 5601 and the 21. Yeah? I don't know. It's possible they were doing some kind of annealing of the learning rate or something like that. Yeah, I can't remember exactly what they were doing during the organization. Whatever they're doing, it seems to affect both curves, somewhat. Yeah. Oh, well, no, that wasn't, no, I was saying it's not overfitting. Yeah, that's my okay, so the same story actually applies on ImageNet. Yeah, so you can see, so this, in fact, you can see it's actually very similar. So if you make the model deeper, the training error gets worse, and then you see the same thing here. The 34-layer model does worse than an 18-layer one. Okay, and so again, what they've done here is to take a certain architecture. Sorry, the text is too small, but basically what they've done is just to add in a bunch of sort of 3x3 convolutions with a ReLU after it. Okay, and so in theory, this model could just construct an identity function. Right? So in theory, this model can represent the functions represented by this one, but this model is better than that. So it's really some sort of optimization difficulty. And they're doing all the right initialization and the right sort of updates and everything. Okay, so this is basically an idea that Kai-Ming He and others came up with a couple of years ago called residual learning. So normally what happens is, if you just take a little small piece of that giant network I was visualizing before, there's the input, you go through some weights, you have a ReLU, you do some more weights, and you have another ReLU. Okay, so this is a little two-layer sort of piece of a much, much bigger model. Okay, now in the residual network, what you're going to do is you're going to basically provide a kind of bypass connection that's going to copy the input here, round to the side, and you're going to add it back in to whatever the output of this is. Okay? So in other words, this piece of network we had before now provides a kind of, what you think about this is, it provides a kind of correction term to what the original input was. Okay? So I guess they call it a residual mapping with respect to the identity. So this is, you can think of this as like an identity function, just copies this round. And then this network here is like you're just tweaking the input through, it's again, little two-layer model. Well, actually, slightly different, sorry. They've actually pushed the ReLU out past the summation and so on. And the basic idea is, like, you could, if you just wanted to copy the input, you could just set all these weights to 0, right? And then you would have a sort of, the gradients would flow smoothly from, when you're doing back pop, you could easily push the gradients back through here, and you wouldn't be sort of, changing things too much. And when you do that, this is a relatively simple change, but a very important one. Basically, because, sorry, just to reiterate the point I sort of didn't explain so clearly, that whole business there of the gradients vanishing or exploding goes away with this thing, because basically this always provides a connection which has kind of scale factor 1 in both directions, because it's the identity function. In practice, that means it just makes these models a hell of a lot easier to train. So this is what happened with the plane networks. Without, this is the ones I talked about before, the training error got worse as we made them deeper. But then what you find is with these residual networks, so they've introduced this sort of bypass connection around each group of layers, then the story is reversed. So now it goes 20, 32, 44, 56, 110. Okay, so now it does actually have lower training error. And what's cool is it also has lower test error as well. So this is also true on ImageNet. So you can see the order of these two curves is flipped now when you use the residual connections. And then they do have some slight practical, they have some practical tweaks to this. So in practice, they do introduce some sort of bottleneck. They find this sort of squashing down. These are sort of dimensionalized reduction layers, basically. Okay, so one-way-one convolution and change the number of feature maps. You can think of, if you didn't have the ReLU here, you could think of this like as being a PCA operation. So it's sort of applying now this convolution in this lower thing and then projecting back. So this is just a way of, in practice, seems to help with. And so this is showing error rate on ImageNet, I guess. So when they had 34 layers, they got 7.4%. You can see them jacking up the number of layers. Again, using these residual connections. Okay, so if you just do it normally, this thing would have a much worse error rate. In practice, you can see with the residual thing, it ends up going down quite smoothly to low error rates. So to be honest, these residual nets can be really, really useful. And not just in the vision domain, they're used in a whole bunch of settings. I think I have slides just discussing that.
So,
yep.
Before we add a convolutional layer and maximum.
Yeah. Right, right, let me just wind back a second. So in this setup here, sorry, it's very tiny text. The pooling operations are, basically we have a few pooling operations every so often in the model. And what we're doing is we have a whole bunch of these layers which are just convolution, ReLU, convolution, ReLU, convolution, ReLU, convolution, ReLU. Okay, that's the structures that people found work really well. And instead of just, what we're going to do is we're going to leave all the max pooling layers where they were, not mess around with them. But those big columns of conv-ReLU, conv-ReLU, we're going to start replacing them now. Instead of being, this is one, little unit, you're just going to replace it with that thing. Okay, so you're keeping the same sort of pooling structure you had before. What you're doing is messing around with these sort of very deep conv-ReLU, conv-ReLU, conv-ReLU stacks. So you'll have many of these bypass connections, right? So it's a figure. Yeah.
How can you go and
Yeah. This one? Yeah.
What if like the FX is like already like a small signal, say maps from 0 to 1?
I'm sorry.
What if FX is like already like a small signal, like a sigmoid which maps from 0 to 1 and then X is kind of big or something?
But what you care about is the, it's not the magnitude necessarily, right? It's also the, it's sort of like, kind of like the Jacobian between the input and output of this thing, right? So probably things like sigmoid is, there are parts of that sigmoid where the gradient is very flat. Okay, so that in practice that means when you go back through the network, it's very, very difficult to actually train because the gradients, the value itself might be sort of close to 1, but or close to 0, but the gradient is actually minuscule in both places, and therefore it's very hard to, when you can stack these together to train. Okay, so this is just, just see how many slides I've got. I don't want to do which one I've got. Just quickly, isn't it? 15 slides in 10 minutes. Alright, I can, I'll go through this. I think it's somewhat relevant. Okay, so there's I don't know if you've read, there's a very cool paper by number 2 which is worth reading about. And he's making the point that there's actually a whole bunch of different factors when you're trying to really get a big machine learning model to work correctly, how it generalizes, how well you're able to optimize that model, and how well that class of models performs in general on your data. And they basically, these deep nets, you can basically have a broader class of models because you can now make them deeper, and then this forward and backward propagation you need to do in these models, because of this bypass connection, which is the density function, makes the models a lot easier to train. This sort of, gives you this smooth. You don't have this vanishing gradient problem anymore. You could have normal of these things. And then in practice, it seems that deeper, thinner models seem to work better. For a given sort of amount of kind of non-linearity, they have relatively few parameters, and so actually generalize pretty well. So you don't get overfitting. And in practice, the way a lot of systems work is you have one of these sort of residual networks that takes in the data, and then you stack on top of it whatever a sort of head for whatever task you care about. Maybe it's detecting objects with bounding boxes, maybe it's segmenting things with pixels or recognizing human photos. So you typically find that they rely on some common trunk, which is one of these networks that was trained originally for classification. So just to show you an example, this is just where you're trying to localize the bounding boxes around. There's models that, again, this would be a residual network, and then they have some way of proposing various regions that could be objects, and then sort of pooling and classifying over those in an end-to-end fashion. This is sort of slightly more recent version, which does more or less the same thing. This is another. This is the same system I was showing you before. This is just some another. This is frame by frame. Okay, and then it's worth also noticing that I'm going to skip over this. So one thing I was just going to show you is that this is a nice sort of way to sort of transition to the next lecture. So everything we've talked about so far is with supervised training. Okay, with very, very deep models trained on millions of images. In practice, that is a limitation. And you can label millions of images, but you can't label like billions of them. Okay, it's just physically not possible. But in practice, oftentimes out there in the world, you can get some sort of noisy source of information about what's in the picture that could act as some sort of noisy label. Okay, so this is a little project that some of the folks at Facebook did. It's at ECCV this year, which I think is quite a good example, and it really illustrates the kind of scale of things you can do with these models. Basically, what they did was, images on Facebook and Instagram, have people put tags on them. Okay, so some of these things, of course, are indicative of what the content of the picture. Other ones, it's hard to. What is the it's not obvious this is a birthday just by the picture. And the key point is here that you can get these things for free. Okay, humans providers may upload them and so on. Right. So the idea is that they're kind of noisy in sometimes. You can get these things for free, but they're, they're a bit messy. And it turns out that these deep nets actually are fairly robust to training off noisy labels. Okay? You might think, well, maybe it's going to screw things up, but actually, as long as if you have like even 40 to 50% noise in these labels, like 40 to 50% of them are kind of just irrelevant, the thing will still train okay. So this was a project they did where they actually took a sort of set of common hashtags that corresponded to actual nouns. Okay, because if you've got a noun like love or something, it's not quite clear what that corresponds in terms of actual image. So they took sort of proper nouns, used WordNet to find sort of synonyms and stuff like that, and then this was an internal project at Facebook, so they actually got all, they got 3.5 billion images of internally, each of which would have these noisy hashtags, and then they trained one of these sort of state-of-the-art ResNet models. This is a sort of a slight twist on the ResNet thing I was just showing you. This is a huge model that has really like hundreds of millions of parameters, and then they slightly changed the loss function, not in any major way. And then they did this distributed training. So they had very large batches. That was that paper I was showing you, training each in 1 hour. So they basically used a batch size of 8,000, spread across a whole bunch of GPU machines. And and then basically they were able to train this enormous model on this 3.5 billion images. It still took a while, but they were able to do it. And this is showing you, so basically the models just keep getting better. So this is the same model trained on ImageNet, okay, training data, which is around about a million images. And this is the top 1 accuracy. So sometimes people use top 5, top 1s. This is the top 1. And you can see that it's doing pretty well. It's going to asymptote to about 80%, no matter how big you make the model. And then this was the data, the Instagram data, which was nearly 1 billion images with about 1,500 different classes. And this is the top 1. And then so what they do, they train this on Instagram, and they would then retrain the final lag or 2 just using the ImageNet training set. So this is like, you think of the pre-train, as it were, on this absolutely enormous collection of data from Instagram. And then this is the performance here. This is different sizes of model. So they're just increasing the number of feature maps, I think, in each layer. And then this is the performance here. So you can see, the biggest models is actually a pretty decent performance gap. And these things, they really do work. They do know, when you look at examples, they actually do work noticeably better than, even state-of-the-art models. This gap, what I'm trying to say is, it may not seem like you think, 5% would do care, but actually, qualitatively, they do actually work quite a lot better. And then, So in other words, these models can really be trained at a huge scale and absorb, billions of images. Okay. So I'll stop there for this lecture, and then does anyone ask any questions quickly? Okay. Sure.
Yeah. So the ResNet supposed to be like a combination between putting long layers together, and also splitting some layers.
Yeah, stick connections. Yeah.
But that's the whole intuition behind it.
Yeah, roughly. I think the major thing is that it just changes how the train is going to operate. You've got this pathway where the Jacobian is 1 back through the network, and in practice that just means that the network trains just a lot better. So the story Canning told me is that he was going to go on vacation, and he had to got each step something running on the cluster, and he thought he would just try this random idea out, and he just set it running. So he didn't have any huge insight. He was just like, it's a bit of a Hail Mary, but we'll try it. He came back like 2 weeks later, and he's like, oh my god, so is that what you're asking?